Let's get into the sufficiency principle. I'll just write sufficient statistics. I'll just put sufficiency. So to encompass sufficient statistics and the sufficiency principle. So the principle says that if T of X is a sufficient statistic, then all inferences based off of T of X have all the information about the parameter set theta. So there's this thing that we have all our X's, X, that's our data. Maybe you're thinking that this thing is X1 to Xn, some vector. This could be any object, really. We're usually thinking about vectors, though, in this class, or matrices or something like that. And I'm going to say that this thing comes from some distribution, theta. So that's what we're going to get. I have a little bit of abuse in notation. This is a random variable. And the book is very specific about the random variable. And I'll spend a little bit of time changing their notation in the book. And then I'll change it to what the book is actually using so that you can pair everything up. I think it's slightly confusing what's going on. So this is the random variable. And I'll say this is the observed data. And let me make that even more clear. I'll say X obs for observed. Okay, so I'll give you a little bit more notation. They use cap X and little x in everything. And so I'll just be even more clear about this. So X obs, that's what you get to observe. So if you have this, you can compute some function of it, T of X. So this is a statistic. So this is just one-to-one. If I have X, I can compute some function of X. If I compute a function of X, I don't necessarily know what X is. So a good example is the Xi's and the sum of the Xi's. So I could have a sum of the Xi's and lots of X's could sum up the same way to the same sum. So we're going to say this is sufficient. So that has a property. So I've just induced a mathematical property on T of X. Keep in mind, this is just a one, this is just, there's no stochasticity here, there's no probability here in doing this calculation. The probability was up here on collected the X's. I've written it this way, is I'm going to collect the whole block of X's so I can get rid of the IID assumption. I don't have to talk about Xi's coming from the distribution and building this up. I'm just going to imagine the whole block that I get. And I've got some model that attaches X's to thetas. So the goal is to learn thetas. So finally talking about inference again. So this is not stochastic. This is not probabilistic. This is probabilistic. So that's where the probability is coming from. Let's just remind us what a sufficient statistic is. So this is the definition. And this is what we get out of the book. It says f of x given t of x. And I'll write it down like this just to keep us confused and put the theta in there. This right here is not a function of theta. So this thing disappears. So how do we build up this distribution? If I didn't know anything about what is on the board, I would write it down the same way that I would say, oh, this is like the joint distribution of f of x and t of x given theta divided by the margin on t of x conditional on theta. So just keep in mind, if I condition on theta there and I condition on theta there, it's conditioned in the result. But what I'm saying is that somehow all the thetas cancel out of this ratio. So what is this distribution right here? This distribution is just f of x given theta. So that's the original sampling distribution. So I'm appending t of x, but there's nothing probabilistic about that. So if I know what the x's are, and I know the probability distribution of the x, then given those x's as well, t of x is just a computation, it's just a calculation. So this is just the ratio of that thing. And it's saying this thing is not a function of theta. And immediately I feel pretty good about this. So when I understand it like this is just the ratio of f of x given theta to f of t of x given theta, and I'm saying this thing is not a function of theta, then I know that there's all the action with theta in the numerator and the denominator are canceling each other. So what that tells me is that the shape of this is a function of theta and the shape of that is a function of theta are the same things, and they're canceling each other. And I remember seeing this for the first time. I was finally catching up in grad school and going, oh, now I know what a sufficient statistic is. And anybody that was an undergrad in stats already knew. I didn't know until I was in grad school. I immediately knew, and probably you do too, is something is factorizing out of this and canceling that stuff. So I can factorize the function of theta out of this, and it's canceling, obviously, because it's coming in a ratio. And it's not a function of theta, so that part cancels. Let's just remember an example, a Bernoulli example. So I'll just say example. Let's say xi's come from a Bernoulli parameter p. So p is my theta. And I'll say we get n data points. And so that means f of x given p is equal to product, I goes from 1 to n, f of xi given p. So this is an independent case, conditionally independent, I can't help myself. So p of xi, 1 minus p, 1 minus xi's. So p lives between 0 and 1. The probability of success or failure, and the xi's are 1 and 0, corresponding to the successes and the failures. So that's the sampling distribution. I'll write it down like that. So, and we might know some of the xi's, I goes from 1 to n, is sufficient. I'll give you a better way at the end of this lecture how to recognize it instantly, where you don't have to just confirm it. But right now I've given you a tool that you can use to confirm something as a sufficient statistic if I hand it to you. So I need to know what its distribution is. So this is t of x in our case, for the example, and I know some of the xi's. I goes from 1 to n is binomial. And this thing looks like this. F, some of the xi's, given p is equal to n, choose some of the xi's. P, some of the xi's, 1 minus p, n minus some of the xi's. You can put any indices in there. That makes you feel better. So ratio of these two things? F of x given p over f of sum of the xi's given p is just equal to 1 over this thing. So just what we had last time. And so that's not a function of p, even though we see the p's on the left-hand side. We can see all the stuff that's factorizing out. So it's really just this stuff. So we can see that factorization happening. That's the only way for it not to be a function of p. So not a function of. So sum of the xi's is sufficient. When I see this, I'm taking this a step further than what the book is willing to do, because I'm assuming a lot of things and taking things for granted. I'm thinking of these as likelihood functions at the end of the day. And just showing that they're likelihood functions, whatever, it's a function of this parameter, we'll call it theta, but theta is p in this example, that they have the exact same shape. And it's that shape that's all the information. Now, of course I like likelihood functions. The book's not saying that. They're talking about all of this in terms of just a probability distribution. But if I know the probability distribution, I know the likelihood function. So for me, it's an easy one-to-one connection. Okay. So that's that. I think this makes sense that they have the same information because they have the same shapes, so it's not a function of theta. So that's at least your intuition. For me, that's almost good enough. They have the same shapes, but somebody might start saying, what do you mean it's a shape of theta? Are you treating that as a likelihood? I don't adhere to likelihoods. And in the 1940s, you might have heard that argument. But nowadays, even Fisher, nowadays Fisher probably doesn't think anything. So, but if Fisher was still here, he would think that likelihoods were maybe not as controversial as he did maybe in the very beginning of everything. So keep in mind, Fisher does utilize likelihoods all the time. So his fiducial argument requires it. I don't teach the fiducial argument because it's not quite right. The correct fiducial argument is probably Bayes, but I don't want to start a huge debate right now. Okay. So let's go through the two experimenter groups. Homework. Two experimenters. I would have felt pretty good about this. If they just would have showed me this in grad school, let's just move on. They have the same information because they've got the same shape. So, but let's just vary in a more correct argument and not just dwell on our intuitions about things. So this is more of a formal proof. So I'll say experiment 1. They get to observe X. That's his data set. I'm going to be more specific and call this X obs. Just distinguish between the observation and the random variable, because I think that's the part that's a little bit confusing. Experimenter 2 gets to observe Tx obs. So I'll also mention experimenter 1 can compute this. So and can compute T of X off. So they know that function too, and can make that calculation. Both of them so here's kind of the fantasy land stuff. So both of them get to know the model. They both have model in hand. So they get to observe this function f of x given theta. So again, sufficiency requires model in hand. So sufficiency isn't a database concept alone, it's data with model. So they get to observe this. This does not mean that they know theta. This means they know a function and a connection between the data and theta. So, and both can compute. F of x given t of x. So they can compute that function. So experimenter 1 and experimenter 2 both know probability theory and can come up with the transform distribution. So again, this is just a mathematical equation that they have. And so they know probability theory and they can come up with this distribution. And they can divide these two distributions. So again, they don't know theta. Or at least I should say, not yet. But they both have the same information about theta. So that's going to be the kicker here. So we'll prove, feels like an important word, both experimenters have the same info. Without theta. Just to remind us here, f of x, for example, given t of x is equal to 1 over n, choose some of the xi's. That goes from 1 to n. We'll point out again in our example, this is a uniform distribution. So it's a uniform over all the vectors of zeros and ones, but it's not just any old vector of zeros and ones. All of those vectors sum up to the same number. So they're all conditioned on the exact same thing. So this part right here is fixed. So this is sum of the xi's right here. And so in terms of everything that we're writing down, this is sum of the xi, and I'll call this observed. So that's the observed sum right there. So this distribution is that thing right here. So I can draw uniformly over vectors of zeros and ones such that all those vectors sum up to the exact same number. So pretty easy thing to do. I could enumerate all vectors of zeros and ones. How many are there? There's n, choose some of the xi's. And I could enumerate all of those vectors on a ticket, drop it into a hat, swirl the hat around, and pull out one of the vectors. The chance that it's exactly the vector in the exact same order that we got to see here is slim. So what's that probability of it happening? So each one of them have the exact same probability. Okay. Here's our proof. So I'm going to say f of x is equal to x observed This is what experimenter 1 gets to see, given theta. Experimenter 1 can form this distribution right here. They know the model, they know the actual data set, they can plug their data set into the model and compute that function. So in our binomial example, this is a probability. In a continuous example, this is a density function. So that's what experimenter 1 knows. I want to convey the point. This is experimenter 1's information. So they've got this distribution. And when we talk about the same information, we all agree, because we're in this class, the information comes through this probability function, or density if it were continuous. That is the information. I understand there's a step that's missing here. What are you going to do with it? And that's where some of the divides live. What you actually do with this distribution. At the end of the day, regardless if we're classicist, frequentist, even though a lot of people, when they say they're frequentist, they don't even know what they're talking about. You know, they have to define what kind of frequentism they're after, what repeated property that they're invoking. So like on a confidence interval, they say, well, I got this asymptotic confidence interval, and it covers at some rate. And you say, well, what's the rate? And they say 95%, and you say, no, that's asymptotic. Is it exact? And if they say they don't know, they're no frequentist. So does that kind of make sense? Dylan says no. What does it mean to be a frequentist? I know you didn't say no, I'm just trying to incite them. I don't know. You don't know? I just told you. There's a frequentist property that you're monitoring. So you have this frequentist notion of probability. Maybe it's relative probability, or the long run average, where you take everything off to infinity, and that's how you're thinking of everything. So confidence intervals, the thing we learned about in Stat 101, where we compute some interval, and then we describe it as the probability interval that covers the truth at some rate. The repeated process is going back out into the universe and collecting more and more data, and then saying it actually covers at some rate. If you don't actually check what the true rate is, I would say you're not a frequentist just because you're invoking frequentist properties. So you're not a frequentist in any practical sense. I need you to actually do the sim study and tell me what the actual rates are. Now, I guess I would say, if you knew that all the xi's were normally distributed and you did the typical thing and constructed x bar plus or minus approximately 2 standard errors, I probably wouldn't ask, did you check the actual coverage rate, because I know they're exact. But in any large scale problem, if you did not check in a real sim study or something like that, I'm going to say you're a frequentist that lives in asymptopia. You're not part of my universe. So I don't know what it all means. That's a mathematical argument, but I'm a statistician. I'm trying to actually make real inferences, not just talk about properties. So that's what I want to distinguish. So this is the information. What does experimenter do with this? We'll learn about that in chapter 7. But the probability distribution is the information. So I'll just point out, this thing is just f of x equal to, give myself some more room. This is f of x equal to x observed. T of x is equal to tx observed. Given theta. So no additional information right here. I've just appended the statistic, the calculation of the statistic. So all the variability controlled the x's, and so the transformation here with the x's in hand, there's nothing probabilistic there. Let's just invoke some basic properties about probability distributions. This is always true. So I'll write down x is equal to x observed. Given t of x is equal to tx observed. and theta times f of tx is equal to tx observed given theta. That's true regardless of anything. That's just a probability rule. It's just our rule for conditional probabilities. Regardless of anything I've written on the board, I would accept this at face value. This is just always true. So now I know a few things about this. I know something about this function right here. I know that this is not a function of theta. The reason we know that is because t of x is sufficient. So we've already said t of x is sufficient. Now we're going to prove that experimenter 2 has the same information about theta. So this thing right here is f of x equal to x observed given t of x is equal to tx observed. No thetas here. F of x, f of t of x is equal to tx observed given theta. So all I've done is get rid of this part. That's because t is sufficient. So I've used that property. I think we know who the experimenters are. Experimenter 1 gets to see the whole data set, can compute the statistics. Experimenter 2 knows some functions, doesn't get to see the original data set, just gets to see the sufficient statistic. So let's just think about this a little bit. This is the hard step in the proof, the conceptual leap that you need to make. So they say experimenter 2 can draw from this distribution right here and create a new random variable. So how are they going to do it? In our example, experimenter 2 is going to go to this distribution and they're going to grab one of those tickets. So they're going to grab a vector of zeros and ones. It might not be the exact same vector of zeros and ones, but there's a constraint on it that they sum up to the exact same number of successes that experimenter 1 saw. So experimenter 2 can draw, I'll say sample, from f of x given tx observed. So I'm kind of shorthanding the notation just for a second here. So they know this function. In our binomial example, they know what that sum is, and they can draw a new ticket. So I'm going to write this down as x star. The book uses y right here. So they call this y all of a sudden. So the book says y. From this, they can just compute this thing right here. F of x is equal to x star. Little y is what the book calls that thing. Given t of x is equal to tx observed. I'll point out this thing is also t of x star. They're the same sums. So that's the key point here, is that this is that. They are the same. So when the book is just flipping the notation around, it's because the things are the same things. And they don't spend enough time probably telling us that's the same thing. And there's this key step here. So what we want to actually point out is this. So this is the key. F of x equal to x given t of x ops. If you want to write in t cap x is equal to that thing, go ahead. You never see anybody write that down. You know, when you're conditioning, you're just conditioning on some number, and we know what it means. But that's the transform random variable. If you want to just keep it in mind, I think we know what it is. The notation's pretty explicit already. The key is that this thing right here is f of x, where x is equal to x star in this same function. And I'll just write down this is equal to t of x star. They're the same things. So let's just come back to our example. Both of them are saying this number right here. So this thing is fixed for both experimenter 1 and experimenter 2. So when they're talking about this probability, they're both talking about this exact same number right here. And that's true of any example that you can formulate. So I'll go through the book's other example with the normal distribution a little bit later. I don't like that example to start out with because they're saying they know how to sample from that distribution. And I'll talk about that on Wednesday briefly. So I like this example because I know how to sample from that. So it's just a uniform distribution. Sam?
So you're saying it won't always be a uniform distribution once you calculate the distribution of the x's conditioned on a sufficient statistic? It won't always be uniform?
Yeah, that's right. It's not uniform for every example. And I'll talk about another example to show us that next time. Okay, so it's not always uniform. It's some function. This one's really easy to compute, but there are more complicated sampling distributions out there. You want an example, normal distribution where we're trying to infer maybe the mean of everything. So we'll look at that example, do another example next time, and get the feel for this. So yeah, not always uniform, but uniform in this case. So these two things are equal to each other, right here. So that's going to be true no matter what the distribution we start from. And that's the key step, is to recognize whatever this distribution is, they're exactly the same, whether or not I plug in x obs or this new vector that experimenter 2 can generate. So experimenter 2 generated this. I'll call them their values. So values on the original little bits that make up that statistic. So ones and zeros is what I'm imagining. So now experimenter 2 has a new vector of ones and zeros, and probably it's different from experimenter 1's. So I'll point out that the book says this is y. Cap y. So that's where the book might be deviating from something that's highly intuitive, is they just call this a new random variable. So I'm letting it be the exact same random variable, and we'll see in a moment they are the same random variables, but I think they don't spend enough time explaining that. So you can call it y, you could call it cap x, and I'm just setting it equal to something different. So you could call this cap y and little y if you want, but it really is just cap x, and I'm just plugging in something new for its value. So that I've sampled from whatever that distribution is. So for the binomial example, it's uniform, so easy to do. So this thing right here is f of, I'm just going to write down right here that this says, here's what I'm looking for. So we're back here. So this is going to be f of x is equal to x star given t of x is equal to tx obs is equal to t T X star. They're all the same numbers. Both of these are the same. It's just the sum of the xi's in our example. So the book right here switches that to a y and says that's equal to a little y. Right there. So this is the part that confused me when I first read through this. Why did they just switch that? Isn't x y? And it turns out, yes, x is y. So they are the same spaces that you're sampling from. But they're just denoting when they write this down. Experimenter 2 followed this slightly different process that they sampled from this other thing. And they want to distinguish that the way they sampled and how they did all of this is based off of that distribution or this distribution in the more general sense. And so they want to give it a different name right here. I'm comfortable if you let that be cap x. They also switched the name over here, and they changed that to a y, and they changed that to a y, and they get rid of this one in the middle, but they're all equal to each other. That part's easy to digest. So this is times, I haven't written down the whole thing, so t of x is equal to t of x obs right here, but I can call that x star because they're exactly the same. That part's easy to follow. So given theta. Now I can put this all back together. The exact same unfolding we did here, we can fold it back up. So this part right here, if I upgrade this all to a random variable, and again, the book likes to call this t of y, if you will, and t of little y. Same stuff. So this right here is f of x equal to x star given theta. I'll do it all in one step. So again, I'm just going to take this part. We're going to upgrade this to a random variable. This is conditional on theta. I can plug the theta right back in here if I want, because it's not a function of theta. We got rid of it right up here, so I can drop it right in there if you like the notation. But it's not a function of theta, so it's just kind of a placeholder for it. So it's exactly this move, but I'm unwinding it, I'm winding it up exactly the same way I did here in reverse. Now I can multiply these two things into each other, upgrade this to a random variable, and I'm left with this thing. If you'd like, that's cap y in the book, and this is little y. I like it like that. So, because I can relate all the meanings of all of those things. They're not unrelated to each other. So, if you like, in the book's notation, fy given little y is equal to theta. So that's how the book concludes. I'm fine with it like that, right here. So the key point is that this distribution is that distribution. So they both have the same distributions. They can formulate it, and so they know the same thing about theta, if they choose to do the same inferential procedure. And that's where we need more guiding lights to know what to do with these probability distributions to really extract the information. Does that make sense? It's a little bit of confusion, but it really is just understanding this process, and they're just giving it some weird name when they sample from this distribution. I think this is the part that they need to dwell on, and they do say it, but it's just like the Sellenberger. Ellen told me the other day, this book is dense. Yeah, it's in the paragraph that they say this. And they say it in a sentence, and I think that they should have said it in an equation all by itself and highlighted it. That would have helped me out. I think after I understood the proof, I said, oh, that would help me out if I understood that. Questions? Pretty straightforward? Cool. Right on. I dwelled on this for at least a day or so. Just thinking about what does this mean. Of course, I can regurgitate a proof and remember where some letters go, but I want to understand the meaning of it all. We'll do another example next time. I want to show you just one more thing, one thing that I've already alluded to. So if T of X is a sufficient statistic, the sampling distribution will factorize in a special way. We kind of know that because in that ratio things have to cancel, so if things are canceling in just the right way, that means you factorize something out. I felt really proud of myself in grad school because I understood the factorization theorem instantly after seeing the definition of the sufficient statistic and understanding what it meant. Factorization theorem. This is an if and only if statement. I'll do one direction of the proof today. To do the other direction of the proof, I have to remind you, what a transformation of variables is. And I'm going to reteach you what they maybe taught you back in Stat 101. So they have the proof concocted with a sum. I'll do it the same way, but if it were in continuous land, all that stuff you see in their denominators are integrals. So we'll walk through the other direction of the proof. Next time it's not too hard, but we have to remember the basic definition of transforms. So factorization theorem. So I'll say f of x given theta can be written as two factors. So this is going to be gtx given theta, a function that involves the sufficient statistic, and a function that involves just the data at hand. So for our example right here, because I've erased this, the constant is just this part, and the functional part is all of this part. So this is if and only if t of x is sufficient. So we'll start with t of x being sufficient and show that the factorization exists. Next time we'll start off by assuming the factorization exists and showing that implies that t of x is sufficient. That takes a little bit longer. So if t of x is sufficient, this is one direction of the proof. So we'll prove that this is true. And for next time, we'll assume the factorization and prove t of x is sufficient. Okay, so if t of x is sufficient, we want to prove star. Star is the factorization. Cool. Okay, this is pretty easy. So f of x given theta is equal to f of x and t of x, no extra information, given theta, which is just equal to f of x conditional on t of x and theta f of t of x given theta. So that's just probability theory. That's always true. T of x is sufficient, so we can cancel that out. So because that's sufficient, this isn't a function of theta, so I can just remove theta from my notation. This is g t of x, given theta, and this is just a function of the data, h of x. So in terms of our example, h of x is just this thing right here. It doesn't have any parameters in there. And the kernel of the function, the stuff that involves p, is that other part g in our example. So next time we'll go the other way. Read through that proof, make sure you remember at least the Stat 101 way of thinking about transformation of random variables, and make sure that you understand the mathematical notation that they're using. That's probably the hard hurdle in any class, is connecting the ideas to the notation that they use. So I like this proof because it's entirely constructive. It tells you how to do it. I really like this, and this is how I recognize that things are sufficient in the first place, is I just run the factorization theorem in my head. And I see what part of everything that I can factorize out, and I can factorize everything out of the function that contains the parameters and the data. So I'm usually just thinking about what part of the data can I not factorize away from the parameters, and that's telling me what the sufficient statistic is. So you can recognize your sufficient statistics by applying the factorization theorem. Just seeing what you cannot factorize away from some minimally compressed dimension-wise statistic. We'll talk about that minimal part next. So there's also a definition. And so we'll have to go through all of that as well. That's it for now, you guys. So we'll come back next time, do this. I will talk about the project. We'll do a little bit of yes, no, maybes. And I'll also tell you the other example that they're using is their first example for sufficiency. I just wanted to switch that example over to this example. It's a little bit easier to conceptualize. So the example that we'll cover next time means that you're going to sample from a distribution that looks like this. E to the minus 1/2 xi's minus x bar squared over sigma squared. I'll just tell you, this part can be, oh, and there's a sum up here. I'll just tell you, this can be factorized outside of a normal, and those of you that have experience working with normal distributions have probably factorized this term out of everything. And so I cannot disentangle sigma squared from this function right here, sum of the xi's minus x bar squared. And so that's telling us that that squared deviation from x bar is the sufficient statistic for sigma squared. We'll do that very slowly, show this factor. We can factorize this out, and it tells us that this thing right here is sufficient for sigma squared because I can't ever disentangle this. I could probably rewrite this as the first two moments. So, and talk about things in terms of the xi squareds and x bar itself, but it's equivalent to writing this thing down. I want to point out that experimenter 2 in the example, I don't know what the normalizing constant is, it's just something. Experimenter 2 is going to have to sample from this distribution, and it's a little bit tricky to do because the xi's have to be sampled from this such that they always sum up to x bar, which is a little bit different. It looks like a normal distribution, but normal distributions don't do that. For a normal distribution, this is usually a mu, and then I get xi's that don't sum exactly to mu, but they come close to it. So they kind of bounce around. So experimenter 2's job in this example is going to be sample the xi's such that there's a hard constraint that they sum up to the exact same number. Now I remember staring at this going, I have no idea how to sample from that distribution. It's not a normal distribution, that's only an approximation. So I'll leave you with an extra credit problem later on where I'll ask you to draw from this distribution. And the answer is Metropolis Hastings. So you could use that as a device to sample from that distribution. We'll come back next time and talk about that a little bit more. And then we'll prep for the midterm. Just keep studying the homework problems. Have a quick glance at sufficiency problems. I'll probably ask you something minor about it. I verify something as a sufficient statistic. I'll kind of say already, I won't have you prove the factorization theorem. I'll probably leave that for midterm 2. So something easy for you to think about. And if you're thinking about what's the hard part of this midterm, it's going to be either proving the delta method or the central limit theorem. And everything else will kind of be about order statistics. Cool. Thanks, you guys. See y'all Wednesday.